medium is dictated by the refractive index. And if it is lossless, the wave will go this way, and if you have a lossy medium, obviously it will decay along the propagation through the medium. So, I mean, further relationship between refractive index and permittivity, permeability, you know. So, now if we put these four combinations into wave equation, so what will happen? Now I took lossless medium, I take K out of the picture to see the impact of like these four cases. So if both of them are positive, so we have phase over there, so we have complete wave, and it is like forward propagating wave. It is propagating in positive direction. And if both of them are negative, you see, negative, negative, negative square, and you get negative. Now you still have phase term, right? But sign is reversed, which means now the wave is propagating in the backward direction instead of forward direction. However, if one of them is negative, then you end up with real part, which means it's pure loss. So once a wave entered into that kind of a medium where one of them is negative, so you get evanescent wave, no transmission, no propagation. Now this is like very famous mu epsilon mu diagram. So these are like four quadrants. Now if we look at over here, it should be like both positive, right? First quadrant. Over here we should have mu epsilon negative, mu positive, and over here epsilon positive and mu negative, and this one is a very interesting thing where we have both negative. So we call double positive, epsilon negative, mu negative, and double negative materials. So we can, in the mu epsilon diagram, this is how we can put all these materials. Isotropic dielectrics, abundant in nature, both double positive materials, we can find lots of materials, all of them, like majority of dielectric. Then for the metals, yes, below the plasma frequency metals behave like a metals, and real part is negative, which means metals at optical frequencies fall in this epsilon negative medium, this second quadrant, and obviously in metals we do not have propagation, it's an evanescent wave, right? Over here, mu negative, still no propagation, evanescence, sorry, there is a typo. So there are very few natural materials like ferromagnetic material, but not abundantly available, but still there are some natural materials available in this domain as well. So now if we look into this, all three quadrants has some natural materials. This thing is very interesting. In nature, there does not exist any material which has both epsilon and mu negative at the same time. So you see, and later we will further look into what is the advantages of having this kind of double negative material where we can have backward propagation, so on and so forth. So until here we decided that there are four types of material, and there is one section of materials which is not available in the nature. Such kind of materials we also call right-handed materials, because you see it follows triad of right hand, you see E, H and K, and such kind of materials we call them left-handed materials because it follows the triad of left hand. Now what are metamaterials? Metamaterials, the word is actually combo of two words. One is Greek meta, which means beyond and after, and material, Latin word materia, which means matter, means beyond natural materials. So if we look up front in the mu epsilon diagram, immediately our mind will go that third quadrant, left-handed materials which are not available in the nature, those should be part of metamaterials. However, this was like initial stuff, and later on, you see, this metamaterials thing does not have a now well-defined generalized definition. So we say anything you can artificially engineer, which can exhibit phenomena or properties which are not available through naturally occurring materials, we will call them metamaterials. So in principle, yes, three quadrants have natural materials, but we can still build metamaterials in those domains as well, and materials which are built for the third quadrant, they are pure metamaterials. So this is like generalized term. So where we have, for material we have atoms, for metamaterials we have meta-atoms. The difference is the size. Atom size is very small. Let's say if you talk about classical electromagnetics, so you see for a visible light you have, let's say you take 500 nanometers, atom size is very small. But to engineer this wave matter interaction, you have to have this meta-atoms comparable to the size of wavelength, slightly lesser than wavelength, but it cannot be very small. So metamaterial is basically arrangement of periodic or aperiodic arrangement of meta-atoms in two-dimensional, in three-dimensional, but they are artificially engineered. So we take away from like EM, yes, we can engineer through metamaterials this light matter interaction for EM metamaterial, electromagnetic metamaterials, but we can build several other types of metamaterials for acoustics, for thermal, for mass mechanical, so on and so forth. Now you see, it's more like a hybrid of, you have some base material, let's say it's air, it could be glass or something, and then you put some other material on top of that. So it's more like a composite material, and now you build some effective mu and epsilon, effective permittivity and permeability by yourself, and you can engineer by changing the physical parameters of those geometrical structures. Wow. Okay. This is, I am putting up front what is motivation of studying metamaterials, what are like applications for them, and then after learning some basics, I will put this slide again, once again, to get you deep into the motivation of learning metamaterials. So you see, for this kind of anomalous behavior, instead of, you see, conventional refraction, we can have now negative refraction. Later on we will see how, which can, then we can also build some, you see, epsilon mu effective mediums, epsilon near zero mediums, epsilon, you see, any type of epsilon and mu combination. And applications could involve in invisibility. You can make some, you see, I can see you because there is a reflection of light coming to me. So if I can divert this reflection, you are invisible to me. So a very simple thing is, if I have something and light goes, and if detector is here, you can see. But if it does not come back, you cannot see it, which means you can make a thing invisible. I just put some crops from news, how metamaterials could lead to invisible tanks and super stealthy submarines. You see, look over there. So they have lots of applications, particularly in the strategic organization, and obviously for some other civil applications as well. Similarly, there are acoustics metamaterials where, for example, in the industries, they want to absorb the noise, to reduce the noise. So you can have such kind of acoustics absorbers, ultra thin sheet-like absorbers, which can, you see, absorb the sound and eventually reduce the noise. So Actually, this is not something in the books. There are lots of companies like Sonoblind, Meta Blocker, so on and so forth, who are actually building metamaterials for the industry for this reduction of noise. Then it comes to meta optics. This is also like one, you can say, a special section of metamaterials where you can have flat or ultra thin metamaterials. And as I have mentioned in that session as well, so if you want to have a microscope, let's say, integrated into your mobile phone, if you want to have a metaverse, AR, VR sets, something like a glass, so you need something very, you see, compact, ultra thin kind of thing. So such kind of innovative solutions are possible through metamaterials. And I have listed bunch of companies which are actually producing metamaterials for industrial grade. And this is like global metamaterials market forecast. So currently it stands at 330 million, and if it reach 2030, it will reach to like 1 billion. So there's a lots of opportunities in terms of if you are good at designing something really good. I would also, later on I will also mention, but you see, most of the people who are in academics and still wanted to have some kind of spin-off and so on and so forth, this is something really possible. You see, I mean, there are always two different things. One, modeling and design, and then fabrication. You go to the foundry. Foundry cannot be hosted inside a university. It can only be done by the industry. Universities are for prototyping, for doing all those kind of things. But for metamaterials also, there are companies who actually model and design. And then they are, you see, linked with the foundries to now, going back to some basics, we learned the motivation and job market and possibility and future of metamaterials. So this whole story was started with Professor Victor, who was a Russian scientist. In 1967, he